99, and this is number 21. Page 799, we're going to look at number 21. So number 21 and 22 are from chapter 15, so that means they have to do with chi-squared. And then number 23 and 24 are from chapter 16, so it's linear regression. All right, so the first one talks about black bears and basically how their movements are governed by the need for food, and that goes into this whole thing that they tried to relocate some troublesome bears, and it says, one question of interest was whether relocation works equally well for male or female bears. What do we think equally well means? Is that chi-squared, goodness of fit, homogeneity, or independence? And before you answer, flip the page and look at the data. It's probably not goodness of fit. It's what? Homogeneity. And that's what question A asks us. It says, for this study, would the question of interest be a chi-squared test of independence or test for homogeneity? So for number 21, part A would be a chi-squared test for homogeneity. Okay? And then for B, we're going to actually carry out that test. So we need to go ahead and make our grid. Okay. Remember, your null hypothesis for a chi-squared test is, or a chi-squared test for homogeneity, is that they are the same, and your alternative hypothesis is that they're different. So it said carry out the test. So we're basically going to carry out a test to see if relocation works equally well for male and female bears. So we're going to say null hypothesis, relocation works the same for male and female bears. And the alternative hypothesis is that relocation works differently for male and female bears. I don't think I need to say it, but I'll say it again. Chi-squared test for homogeneity. I guess we never said chi-squared test up top for part A, so it makes sense to put it in there. Okay. Now our conditions for homogeneity are a little bit, just a little bit more expansive than they are for independence. Remember, homogeneity requires independent random samples, so we'd have to assume the independence of male and female bears, right? So our conditions, we would say independent random samples of male and female bears. Okay? And the second one, that the sample is large enough, every expected cell count is greater than or equal to 5, so we're gonna plug this in the calculator and see if we kind of refresh our memory on how to do that, okay? So we say sample is large enough that every expected cell count is greater than or equal to 5. Okay? And so what I'm going to do is because I don't have this here, I do have to show the expected counts. So I'm going to put this up here too. So we've got, what, successful, returned, and nuisance. And then male and female. And these are expected counts. So I'm going to put them in there after I plug this into my calculator. So let's remember how to put this in the calculator. Chi-squared tests for independence or homogeneity all go into the matrix function in the calculator. There are 3 rows and 2 columns. So this is a 3 by 2 matrix. Now remember, for the test for homogeneity, you don't have to do anything with the expected counts. The calculator will do it for you. So we're just going to put in all the observed counts. If I say bless you, that'll show up on the thing. That's all right. The Amber Alert went off on my phone during first bell, so you guys can watch that. Did you guys get the Amber Alert earlier? Yeah. So there you go. Well, the funny thing about the Amber Alert was the first one I got said Amber Alert, and then it said no information. Yeah, it's like, okay, that's kind of pointless. All right, so all this data is in matrix A, and now we're going to put this into our chi-squared test. So we go into stat, test, chi-squared test is letter C for me. Observed is in A, expected it's going to put into B, and then calculate. So I guess I should copy down my test statistic and my p-value. So my test statistic is 10.43 and p-value is 0.005. My degrees of freedom should have been 2, and alpha is 0.05. Now before I finish off this test, I'm going to go ahead and put in my expected cell counts. What was it? Oh, it's 0.01? Oh, thank you. I did not catch that. No, that's good. All right. So now we're going to go back in to matrix and just look at matrix B. And matrix B will be my expected cell counts. So I'm going to round this off to 1 decimal place because I think it's easier. And I think I did this already. Yeah. So this is 26.8, 22.2, 43.3, 9.9, 35.7, and 8.1. Okay? And there's my expected cell counts. And that's just directly from my calculator. Okay? Yes, on the TI Inspire, there's an EXP MAT, right?
Well, yeah. Plug it in the matrix, and then you define it as a variable, and then you calculate it, and then you do stat.
And you go look at that variable? Yeah. Okay. So plug it in the matrix, do the test, and then go back in and figure out what that variable is that you defined as your expected matrix, and then you can look at it, right? Yeah. There we go. If you don't figure that out, Alex, I'll send her over and she'll take care of it. Okay? All right. So 0.005 is less than 0.01, right? So that means we still reject the null hypothesis. P is low, reject the ho. Yep. All right. So we reject the null hypothesis. There is enough evidence to safely conclude the alternative that relocation works differently for male and female bears, right? So there is enough evidence to safely conclude that relocation works differently for male and female bears. Okay? So let's move on to, what, were you using it before? Oh, that was me, I'm sorry. Number 22. He's like, oh, that was dirty. All right, number 22. I don't think that's possible. All right, so it says that they're interested in these hunting strategies of predators, and they say, do predators take the first prey that comes along, or are they selective? So it said in a study of winter prey selection in the national park, radio-tagged cougars were observed to have killed prey according to the table below. So, or the table's actually above, but you can see it. It says at the most recent census in the national park, there are about 3,500 white-tailed deer, 1,000 elk, and 500 moose. Do these data provide sufficient evidence at the 5% level that the cougars are not selecting their prey at random? That is there evidence that the proportion of deer, elk, and moose killed by cougars differ from the park population proportions? Okay? So, here's what we have to do. This is a chi-squared goodness of fit test. And how you recognize it pretty easily is that we have multiple proportions. And you can see that it's not given in a table that's got multiple rows and columns. Wow, that is all sorts of jacked up. Let's try that again. That's close enough. All right. So this is a chi-squared goodness of fit test. So the one thing that's not fun about the chi-squared goodness of fit test is you have to define each proportion. So we only have 3 proportions here, which is nice. There aren't like 8 or 9, but we have to define them all. So P1 is the true proportion and then we have to think about this because this is prey that were killed by cougars. So it's the true proportion of white-tailed deer, or we could probably just say deer. So P1 is the true proportion of deer killed by cougars in the park. Well, yeah, it's to one park. We can't draw this to everything nationwide. We just draw the conclusion to just this park. So yes, probably need to say in the park. P2 is the true proportion of, what was next, elk? Elk. And now we can use our quotes. And P3 is the true proportion of moose. Okay. Is plural of moose moose? Yeah? That's what I thought. Meese. Meese. Yeah, I like it. Meeses. No, all right. So for the null hypothesis, I have to say what P1 is, what P2 is, and what P3 is, right? So I do this based on my numbers I have here. So I have 3,500 white-tailed deer, 1,000 elk, and 500 moose. See, it's not mooses. And 500 meese in this park. So there's 5,000 of these animals, right? So 3,500 over 5,000 is 70%. So P1 should be 0.7. P2 is 1,000 over 5,000, which is 0.2. And P3 is 500 over 5,000, which is 0.1. Okay? That's your null hypothesis. Now our alternative hypothesis for a chi-square goodness fit test is at least one of these proportions differs from the population. Or you know what, let's not say that. Let's say differs from the null hypothesis. That sounds better. That sounds more logical. So it differs from the null hypothesis. Chi-squared goodness of fit test okay. The conditions are real easy. So your conditions now the first one here says it should be a random sample, but it doesn't appear to say random anywhere within here, does it? So I think we're going to assume that this sample is representative of the population of, you know, animals killed by these cougars. So assume sample is representative of the population killed by cougars. And maybe I went into a lot of detail with that, but I'd rather go into too much detail and then not have the context and get dinged for that. The only time it's an independence condition is for a test for homogeneity. All the rest of them don't, because the test for independence doesn't make sense. And here we're just doing one sample, so we don't have two independent samples. Like I'm not looking at cougars and wolves. I'm just looking at cougars. Okay. All right. The second condition, sample is large enough every expected cell count is greater than or equal to 5. Okay, and for this one, I'm going to have to calculate the expected counts. All right, and it's not that big of a deal. We had 128 total, right? So there are 128 total animals. So my expected counts would be 128 times 0.7, which is 89.6. So let me see here. If I'm going to do this, I'm going to say you could put expected frequency instead of counts if you wanted to. So the first one, oh, wrong button. The first one is 89.6. For elk, it should be 20% of 128, so 128 times 0.2, which is 25. I should have been able to calculate that. 25.6, and this is 12.8, right? That's 10% of 128. So these expected cell counts for goodness of fit test you have to calculate on your own. Okay? Now how do we do the chi-square goodness of fit test? Well, you can do it by hand, which is a pain, or we just do it in the calculator. Okay? So for this one, we press Stat, and we go over to Edit, and we enter our data. Oh, I got a lot of stuff in here. Let me clear this out. We enter our data into list 1. So in list 1, I'm going to put in 118, 8, and 2. Okay? In list 2, we put in our expected counts. So that's where the 89.6 goes, the 25.6, and the 12.8. Okay? was that one? There we go. All right, so that's even bigger. Okay? So now what we want to do is the chi-square goodness of fit test. So all I have to do is go to stat, test, chi-square goodness of fit test. That's letter D for me. Okay? Observed is in L1, expected is in L2. What's my degrees of freedom here? It's 2, so it's the number of categories minus 1. And I'll calculate this. Okay? So this tells me that my chi-squared test, did you guys get a test statistic this big? Is this right? Okay. Just making sure I didn't do anything wrong. Test statistic is 30.2. My p-value is essentially 0, right? So my test statistic chi-squared equals 30.2. My p-value, I think it's safe to put that it's approximately 0 when it's times 10 to the negative 7, right? Have to list degrees of freedom. And alpha, I think, was 0.05 for this one, wasn't it? Okay. So it says, do the data provide evidence that cougars are not selecting their prey at random? I think we can answer that question here. We reject the null hypothesis, so link the p-value for alpha. 0 is less than 0.05. We reject the null hypothesis. There is enough evidence to safely conclude that the cougars are not selecting their prey at random. Because if they were selecting them at random, we'd expect the proportions to be really close to these proportions, right? But they're not close to these proportions. They're pretty far off. They're, in fact, way off. Okay? Does that make sense? So what does the chi-square test statistic show? Let's draw this. You know what? Let's not draw that because you won't see anything. Let me show you what it shows. The chi-squared test statistic. If you look at your chi-squared distribution, it looks like this, right? And imagine I gave this this analogy before, but I'll give it again. Imagine I'm rolling a dice, and I roll it 600 times. We expect that I get 100 ones, 100 twos, 100 threes, 100 fours, 100 fives, 100 sixes. But we know that for that to happen, that's kind of rare, right? So instead of getting exactly the same data, it's going to vary. If I get something that's just a little bit away from what we expect, you know, that's still going to give me a lot of area, okay? But if I get something really far away, like way out in here, okay, the upper tail, the positive value from the test statistic up, so this is where chi-squared falls, that gives me my p-value. So this area underneath here is our p-value. So the higher chi-squared is, the smaller your p-value is going to be. The smaller chi-squared is, so if I have a chi-squared way back down here, say, this p-value here is going to be all of this area, so it's going to be humongous. Okay? So the bigger chi-squared is, the less your data actually fits what it's supposed to. The smaller chi-squared is, the better your data fits. Because chi-squared is calculated as the sum of the observed cell counts minus the expected squared over the expected. So if that sum gets really big, it means that these two, observed and expected, are getting really far away from each other. Okay? Oh, the mic's good. I had to turn it down when I listened to the other one. All right, number 23. 23 should be pretty quick. Okay, it says in a random sample of large cities around the world, Y equals the ozone level in parts per million, and X equals population in millions were recorded. And it says, fitting the simple linear regression model gave the estimated regression equation, Y hat equals 8.89 plus 16.6X. So it says, how would we interpret the value of B equals 16.6? Okay? So B is the slope of our regression equation. So we would say that as population increases by 1 million, right? And that'd be people. The ozone level increases by 16.6 parts per million. Okay? That wasn't too bad, right? So now it says substituting X equals 3 into the estimated regression equation gives you Y hat equals 58.69. So give two different interpretations of this number. Okay. So one is, I think the two different interpretations are kind of silly. It's a predicted value. The other way to say it is an estimated value. Generally we say predicted. So we would say the predicted ozone level when the population is 3 million. And the other way to say it, I would say, is the estimated ozone level. Okay? It's the same thing. Yeah. I always use predicted. I think predicted is way better to interpret that. So it says, do you think this equation should be used for predicting ozone in small towns in Iowa? And if you read the first sentence, it says, in a random sample of large cities around the world. So I think the only thing we can use it for is large cities. So the answer here would be no. And this kind of is the danger of extrapolation. We're just not saying that. But, you know, we only sampled large cities, so we can only leave our predictions to large cities. Okay? And it says the value of r squared is not given here, but explain how you would interpret r squared value in the context of the problem. So we don't know what it is, so we would just say it's the percent of variability in ozone level, or predicted ozone level, that can be attributed to the linear relationship between, what is this, population and ozone level? Okay. So that takes care of 23. 23 I don't think was too bad. All right, so moving on to 24. Knocking it out. Yep. All of 24. What do you just want to do the first one? They go until the bell, which gives me about another 12 minutes, man. So I'm good. I got this. All right. So 24, it says below is a scatter plot and computer output for regression analysis of body mass versus wing length for a sample of moths. So you have this whole long thing here. It gives you a ton of stuff. And if we're looking here, there's a whole bunch of stuff that we don't need, but let's make sure we understand what we do need. So let's look at this real quick. All right? So let's see what we do need. So this here is our regression equation, right? And if you forget where A and B are, well, negative 1.221 is here. It's also right here. That's our estimate for the y-intercept, okay? Positive 0.057 is here. Okay, let's go over the important stuff that's in here. Now, they've listed r squared up here and s right here. This is s sub e, the standard deviation of the residuals, and we'll go over that in a second. Okay. When it goes through analysis of variance here, this gives sum of squares. You actually don't need to know any of this, so this really isn't a big deal for you. Okay. Also gives us standard deviation of B, test statistic, and p-value. Where a lot of people get confused is if you notice B and C are saying carry out a model utility test using the 5% significance level, and then C is saying calculate and interpret the 95% confidence interval. A lot of people want to use this for your confidence interval. You can't use that. That's not the same T critical value. You have to think about how they're calculated. For a confidence interval, we use our table and find our 95%. We use, let's see here, we use this table. And we find, our 95%. Oh, that's the wrong table. That's Z. Here's T. And we find 95% on here, and then work our way up to wherever we need to be based on degrees of freedom. Okay? For a hypothesis test, that's calculated, and it's real simply calculated. The test statistic is always B minus the hypothesized value of beta over S sub B. Well, B is whatever it is on there. So in this one, it's 0.0573. The hypothesized value for beta, well, always our null hypothesis for beta is 0, isn't it? So this is actually B minus 0 over S sub B. So in this case, B is 0.0573, and S sub B is 0.0072. When you divide those two, you get that 7.9588. Okay? That's the difference between this, whereas if I was doing a confidence interval, and let's look here, it says, when it says total is 27, that's the total number of dots we have on the paper there, so it means our degrees of freedom is 25. So degrees of freedom 25, 95% confidence, I should be right here. Okay? Does that make sense? All right. Degrees of freedom is not listed. Well, oh, I'm sorry, that is degrees of freedom. So degrees of freedom is 27, not 25. My bad. Okay? All right, so it says, what's the equation of the estimated regression line? And we have to write this out. We have to write, so for part A, we have to make sure we put this in context. So we would say predicted body mass and it's so important to have predicted or estimated, but I like the word predicted better, is equal to negative 1.211 plus 0.057 times the wing length. Okay? Has to be in context. Again, if it's not in context, you don't get credit. All right. There is no way to carry out this test and actually check the conditions. Okay? So we're going to carry out the test, but we're not going to be able to check the conditions. Does that make sense? So let's carry out this test real quick for part B. Oh, that's terrible. It disappears. It's kind of weird. All right. So we have to define beta. Okay? Beta is the true linear relationship. So beta is the true linear relationship between the body mass and wing length of a moth. So our null hypothesis is that beta is 0, and our alternative hypothesis is, I don't know what. Let me read that again. So it looks like we're doing a not equal to test here, because it's not telling us anything else. So we're saying not equal to 0. Saying there either is or there is not a relationship. It didn't say anything about positive or negative. It's just saying whether or not there's a relationship. Okay? This is a linear regression t-test. I'm not going to fill out any of this top right conditions. We're just going to leave that blank. Test statistic. Or I guess we could say assume that met and verified. I won't leave it blank. T is equal to, and we need to go to the table here, so it's T ratio for B, it's 7.9588. Our p-value is also on that table, and that should be really, really small. It says it's less than 0.0001. So if it's less than 0.001, we're just going to say it's approximately 0. We're almost 8 standard deviations above the mean. That's going to be less than 0. Okay? Yeah. Yeah, we don't have to multiply by 2. It appears they've calculated not equal to. 0 times 2 is still 0, so we're good there. Alpha, they said 0.05, and our degrees of freedom should be 25. This computer output's kind of weird. Let me look at this versus the other one just to make sure I'm not reading that wrong. I know, I want to read this to make sure that the degrees of freedom is not wrong. Sorry, the degrees of freedom should be, I'm reading this wrong. Degrees of freedom should be 26. It's the second one down. That's the right one. Sorry about that. I want to make sure I'm reading it right. It's just the way the output is. This is kind of weird. So when you look at this, it says model error total. I had to look back to remember, actually. The book does this. I haven't seen this on the AP exam in a long, long time. This one right here, 26, is where your degrees of freedom falls. But nothing else up here is necessary. I don't think this would come up. I don't think they'd give you that. But generally, they'll tell you just how many are in the sample and know that it's n minus 2. I think that's probably more important to know. Okay. So our conclusion is that 0.05 is less than, I've got that backwards, 0 is less than 0.05, reject the null hypothesis. There is enough evidence to safely conclude that there is a linear relationship between body mass and wing length of a moth.